Okay. I don't have a mic, so I'm just recording this on my phone. So to start, I'm just going to show you the results of the assembly bouncing ball program, and then I'll break down how the code actually works. So right here you can see it is just this one little pixel. I can follow it with my mouse, but it bounces around the screen, and it has collision physics with the sides of the screen. It is very tiny, but it is functional and it's entirely in the hack assembler. So I'm gonna explain the assembly code in kind of a non-linear way. I'm not just gonna go top down and explain what everything is. I'm gonna just explain to you what the program does. I have a lot of comments here. I can kind of talk about those, but those are pretty self-explanatory for the most part. Yeah. So to start, you can see here that the program has a tick delay. So right here, I'm setting that to the address of 4000. So that's just the value 4000. And so then I have tick counter, which is the value of tick delay. And then every time main loop goes, which is the main, you can see the main rendering and physics loop of the program. Every time that goes, it's actually going to only advance every 4000 times. So we subtract that by 1, and then we jump while it's still greater than 0. So only once that hits 0, we're going to keep going through this. Otherwise, it would run way too fast if it was just running by the CPU clock cycles. So for our ball or pixel, we have an x position, a y position, an x velocity, and a y velocity. The position just starts at 10, 10, so that's 10 pixels, x and y away from the upper left. Back in the main loop, every frame we're going to add the x velocity to the current x position and the y velocity to the current y position. And then the collision is here. I have it bouncing if the y is greater than 254, so that's 255 or above. I don't want it to hit the 256 because that's the bounds of the screen. And then I also bounce if it's less than or equal to 1, so I don't want it to hit 0 either. Then I also bounce the x here. And what these are doing is these are jumping to these tags, which are bounce x and bounce y. So for bounce x, it goes to this bounce x label. This is how you implement just doing a negative of a number, so we need to invert the x velocity or the y velocity depending on where it bounced to make it reflect off the edge. And so to do that, for 2's complement arithmetic, you do a bitwise not on that x velocity value and then increase it by 1, just add 1 to it, and that will get you the negative. Then it skips the bounce y because we don't want that to fall through, so it goes over here to don't bounce, which is the same thing that happens if it's not supposed to bounce at all. And then bounce y is the same thing, but for the y velocity, so that's if it bounces on the top or the bottom. And that is pretty much it for the physics and just actual like math side of things. And the rest of it is a lot of rendering, which is pretty hard with the system we're given in the hack assembler. So I will kind of show you how I do that. So right here in the code, I have highlighted for you where I wrote the formula for indexing a specific pixel on the screen. And it's actually, this is just how to get the right machine word. So it's 16384, which is the screen, the start of the screen in the memory. And then the y value times 32 to get the right row. And then x divided by 16 to get the right column. And then what we actually need to do later is to get the right specific pixel, we're going to need to use x modulo 16, but I will get more into that later. All you need to know right now is that this is how we're going to get the right region of the screen to write our little ball into. If I comment out the part of the code where I set the last machine word that the ball just left to white every time the program ticks, you can see that the ball just draws a line across the screen. And while that's kind of cool and lets us kind of trace the trajectory that the bounces are taking, it doesn't look like a bouncing ball. It does make a pretty cool pattern though. So that's why here we check if we have not yet calculated the offset result, which is the specific machine word to index. And if that is empty, then we do not need to do anything, but otherwise we reset the previous pixel to 0, which represents white. So now we do need to start calculating that offset. So the things we're going to need is 16 through 84, which is easy because that's just the address of @screen. And then we need y times 32. And we need, it's actually more descriptive to say floor, which just means rounding down, x divided by 16, or integer division, x divided by 16. But let's start with 16 through 84. So we just go @screen d equals a to get that. So that's our first value, and then offset result, this is where our whole calculation is gonna go. So we put that in the memory there. Then we get the value of 32 and put that in the counter here. And now we do our multiplication. So multiplication in assembly can just be implemented as a loop of repeated addition. So we have our result here, and then we grab the value from that. We add our y to that, and then we decrement that counter, which is going to be, remember, set to 32. So this is going to run 32 times, so it's going to be y 32 times plus 16 through 84. And then at the end of this, once that counter hits 0, we jump while it's still greater than. But once that hits 0, we're going to fall through here. And so now, in offset result, we have added y times 32 to that. And now I need to get the result of integer division x by 16. And also, as part of this division process, I can set aside the remainder for the bit offset, which I will explain in a second. So here, I'm dividing x by 16 and setting aside the remainder. So conveniently, x's address is 16, so I can just use that as the divisor here. Once the remainder minus 16 is less than 0, which is just a way to check if the remainder is currently less than 16, we end the loop. Otherwise, we update that subtracted value in memory and go to the start of the mod loop unconditionally, only breaking once the remainder is less than 16. Meanwhile, we're incrementing the div result at each step of the process, which gives us the result of the integer division. Now we add the result of the division to the offset, and we almost have everything we need. But we do need x modulo 16, and specifically a binary number where there's a 1 at the position x modulo 16, which is the remainder left over after you divide x by 16. So that's what we saved over here in the remainder register. So now I need to explain my answer to this problem, which was bit masks. There's a lot here to look at, but the important thing to note is these decreasing powers of 2, from 2 to the 15th all the way to 2 to the 0th power, which is 1. So 1, 2, 4, 8, and so on. Back here at the bottom of my program, by going to the last bit mask and subtracting the current memory address by the result of x modulo 16, which is that remainder here that we picked up from in the D register, I can then write that mask's specific value with a 1 at the position of x modulo 16 to the address of the exact offset that we need. And with that, we draw our pixel at that x and y value. And with all of that put together, we get our program, which again, just looks like this. Just looks like this. Very simple. If anyone has any questions or anything that they would like the real in-person me to answer when I show this in class, I'm happy to, or if I'm also happy to not take up too much of the class time and talk to anyone after, shoot me an email or whatever. I found this very interesting to make.